Hello, welcome to the new lecture of the course Transportation Network Analysis. So, in the last class, we were discussing about convex combination algorithm. We had just seen an example for that. So, just a small discussion is remaining in that example. So, if we plot how does the objective function value progresses with the number of iterations. So, you can see here on this figure, we have the objective function being shown on the y axis, and we have the um, number of iterations on the x axis. So, you can see here that, for example, in the first iteration this is the objective function value that you get, but in the second iteration this is what you get, and in the third iteration this is what you get. This difference between first and second is larger than what you will see in the objective function value as you compare between iterations second and third, and again this one will be larger than what you will be getting later. So, you will be seeing that there is this asymptotic reduction in the objective function value as the iterations proceed. What it means is that the marginal contribution of each successive iteration becomes smaller and smaller as the algorithm proceeds. Okay, so in the beginning we will be seeing larger reductions in the objective function value, but as we will move forward these reductions will slowly reduce. Okay, so this is one characteristic of the convex combination algorithm. One thing we have which we haven't discussed until now is that suppose that the objective function that we are focusing on is having convex objective function and it has linear constraints, then if we perform sufficiently large number of iterations, what is the guarantee that it will reach to the optimal? So, since this property has to be verified for every instance of the problem, that is every possible example, so the only possible way to argue this is through a mathematical proof, okay, because there are infinite such example or instances. So, it is not possible to argue for each of them that this algorithm will be reaching to the optimal solution if sufficiently large number of iterations are carried on. So, there is a proof of convergence behind that, but due to the shortage of time we will not be discussing that proof, but it is available in such standard references which are being mentioned here. Okay. So, with this we kind of complete the discussion related to convex combination in the general case, and now we will be using this convex combination method to solve the user equilibrium problem. Okay. So, the reason why we had digressed towards learning these optimization algorithms while we were discussing traffic assignment was to develop efficient methods for solving the optimization formulations of various traffic assignment problems like user equilibrium, system optimization, and so on. Okay. So, again we are now coming back to that main goal of solving these traffic assignment problems using efficient algorithms. So, let us recall the Beckmann's transformation for user equilibrium, or which is the optimization formulation for user equilibrium. So, this we have seen before. So, I hope this does not need to be explained. So, this is the objective function and these are the constraints here. So, one thing to notice here is that the objective function is convex, and we have actually seen this before. So, when we were deriving the first order conditions or the KKT conditions for user equilibrium, so there we had argued that the objective function is in fact strictly convex everywhere. If it is strictly convex everywhere, it is also convex everywhere. So, therefore, the objective function is convex. Okay. So, we will not be arguing that again. So, there when we were doing this argument to argue that the objective function is strictly convex everywhere, we had looked at the Hessian matrix and we had argued that it is positive definite. Okay. So, that is how the proof goes, and the other part is that the constraints that are present in the user equilibrium formulation are linear. Okay. So, this is linear constraint, this is linear constraint, and this is also linear constraint because these delta AKRS, these are known parameters. Okay, because these can be determined from the network structure. Okay. So since this optimization formulation for user equilibrium is having convex objective function and has linear constraints, it is possible to use convex combination algorithm to solve it. One more thing is that although any other optimization formulation which need not have convex objective function and linear constraints can also be targeted through convex combination algorithm, but the thing is that this algorithm may not have the guarantee to reach towards optimal when sufficiently large number of iterations proceed. Okay, so that is why this fact that the optimization formulation of user equilibrium is having convex objective function linear constraints is helpful in the sense that we will be sure that when we use this convex combination algorithm, we will be reaching towards the optimal solution. Okay. So therefore, we can apply this convex combination algorithm to solve this problem. Okay. So in the first step of the convex combination algorithm, we have to find the descent direction. Okay. So there we try to minimize this objective function. We have seen this before, subject to the constraints that this new auxiliary solution y is a feasible solution. Okay. So at the nth iteration of this algorithm, we already have the idea of the current solution that we have, this xn. Okay. So this is the gradient of the objective function at the current solution, and this is the dot product with the auxiliary solution y that we want to find. Okay. Now in user equilibrium formulation or Beckmann's transformation, the decision variables are the link flows. Okay. So therefore this gradient function, gradient z xn, this will have as many number of components as the number of links that are there. Okay. And similarly this yt will be having what? It will be having y1, y2 till ym, suppose where m is the number of links that we have. Okay. So the number of components that are present in the gradient function as well as those in this y transpose function, they will be the same. Okay. So this dot product actually is this summation here where we are multiplying the partial derivative of this function z with respect to the flow on link A times ya, which is where ya is the auxiliary flow through link A. Okay. So since we know what is the objective function in the user equilibrium formulation, let us simplify this expression here that we have seen. So now we are replacing zx with this objective function of Beckmann's transformation. Now you can see here that when we go from here to here, the summation is gone. The reason behind this is that the travel time on any link is a function of the flow through that link only. So only when the link here is the same as this link, only then the partial derivative will be non-zero. Otherwise this whole term will be not a function of the flow through link A. Okay. So that is why there is a single term here, and then we see from the fundamental theorem of calculus that we get this when we take the partial derivative of this with respect to xa. Okay. So this is the travel time function of link A when the flow through it is xa. Okay. So this is what it is saying. So the second equality from the left, which is this one, holds as travel time on a given link only depends on flow through that link. Okay. So this is what I had said, and the third equality from left holds due to fundamental theorem of calculus. Okay. Okay. So now we have simplified this partial derivative of this function z with respect to the flow on link A as this. Okay. So now we can put it back into this. Okay. So now since the partial derivative of this function z with respect to the flow on link A is Ta xa n, and since we know what is the solution at the nth iteration, so therefore the travel time of link A at this iteration is also known quantity, because the flow through link A is known at this current iteration, because we know the solution xn. Okay. So that is why this quantity is a constant which can be represented by this tan. Okay. Okay. So therefore, the linear program for finding this descent direction is as follows. Okay. So we have this as the objective function. So we have replaced now the partial derivative of the function z with respect to the flow on link A by this constant TAN, okay, times YA, where YA is the auxiliary flow through link A, okay. And then we have the usual constraints of the user equilibrium formulation. Now you can see here that instead of FKRS, there is this GKRS variable, okay. The reason behind this is that this is just to differentiate that this optimization formulation is not the same as the user equilibrium formulation that we had. So therefore, these variables GKRS, although it's representing the auxiliary flow through link through flow through path K connecting R to S, but it is not actually the flow that will be existing on path K connecting R to S in the user equilibrium solution, okay. It is just the flow through path K on origin R to destination S for this optimization problem, okay. So just to differentiate that fact, this FKRS has been replaced by GKRS, and similarly instead of link flows XA we have YA here, okay. So here you can see that this is having almost the similar constraints as the user equilibrium problem. The objective function looks slightly different, okay. Now let us try to understand what this optimization formulation is. So one thing here you can notice is that this objective function slightly looks similar to the total system travel time function that we had in the system optimization formulation. So you remember there was this function XA TA, but there the TA was a function of XA and we were summing this over all the links A, okay. Now there is a difference that instead of this TAXA there is a constant TAN, okay. So the travel time on a link K is kind of fixed, okay, which is given by TAN, okay. Now when you have the travel time on all the links to be fixed and you are trying to minimize this total system travel time subject to these constraints, then how do you get the solution of this? Now if you remember, we had discussed that there are some special cases when UE solution becomes equal to the SO solutions. So one of the special cases when this happens is that when the flow through the network is very less, or when you can assume that the travel time on every link is independent of the flow through that link, that is, it is constant, okay. So that is what this situation is exactly is, that here the travel time on any link is constant, okay. So if that is the case, then whether you look at this formulation as a system optimization formulation or a user equilibrium formulation, it will be the same, okay. So now in order to understand the solution of this optimization problem, try to think it in this way, that now the travel time of each link is fixed, which is given by TAN here, okay. Now since this optimization formulation is also equivalent to the perspective of user equilibrium, so since the objective in the user equilibrium is that everyone tries to minimize his or her own travel time, now if the travel times do not change with the flow, so then everyone would want to travel on the path that is offering the shortest travel time, right. So therefore the solution of this optimization formulation is to assign everyone who is traveling from origin R to destination S on the shortest path which is connecting R to S, okay. So this is actually the simple solution of this optimization formulation. So this is just defining the variables here, which I have already said that Y is an auxiliary variable which is representing the flow on link A, and GKRS is the auxiliary flow variable for path K connecting OD pair RS. And here the objective function TA and YA summation over all links is the total system travel time when the link travel times are fixed, that is they are not flow dependent. Okay. Why is that? Because you know the solution at the nth iteration, so you know the flow through every link K at this current iteration n, so you know the travel time through every link K. Okay. So therefore, this total system travel time in that optimization formulation that we just saw, where the travel times are fixed, can be minimized by assigning all the travelers to the shortest travel time path connecting every origin to destination. So this is what I was saying, that the linear program that we saw for finding the descent direction has a very simple solution, because the travel times, all the links are fixed. So then everyone would want to travel on the shortest path connecting their origin to destination. So all the demand that wants to go from particular origin R to destination S, assign it to the shortest path which is connecting that. Okay. So this kind of optimization program is called all or nothing assignment, all or nothing program. And the score of all or nothing procedure is the determination of the shortest paths between all the OD pairs. Okay. We can just quickly take a look at this example of how does this all or nothing works. So for example, suppose there is a simple network here. Okay. Suppose there are these nodes A, B and C. Suppose there are 4 links here represented by 1, 2, 3 and 4. Okay. And suppose the travel times of these links are as follows. The travel time of this link is 5. So this is a constant value. The travel time of this link is suppose 2. The travel time of this third link is suppose 1, and the travel time of suppose this link is again 2. Okay. Now suppose there are 2 origin destination pairs. One is from A to B. So there 2 units of flow is taking place, and the other is from C to B, where 3 units of flow is taking place. Okay. Now suppose we have to do the assignment of this flow using all or nothing program. Okay. So then all the flow that is taking from A to B will be traveling on the shortest path, that is this 2 units that we have will be taking the shortest path from A to B. Now the shortest path from A to B is actually to take this link, link 2 and then link 3, because it is offering the total travel time of 3 units, which is the least, because it is lesser than this and it is also lesser than traveling to link 2 and then link 4. Okay. So all the travel demand from A to B travels through link 2 and then to link 3, and for the demand which is going from C to B, everyone will take this link 3 rather than link 4, because it is offering shorter travel time than this. Okay. So now with this, if you have to determine the link flows in the all or nothing assignment, so how do we do that? So the total flow through this third link here, this one, will be what? It will be equal to the 2 units which are traveling because of A to B and the 3 units which are traveling because of C to B. So total of 5 units is traveling on the link 3 here, and the number of units of flow that is taking place through link 2 is 2 units because of this flow, and all the other 2 links, the flow that is taking place is 0. Okay. So this is the how we calculate the solution of all or nothing assignment. Okay. So although this all or nothing program is a linear program, so it's not very difficult to solve, but an alternate procedure is to solve it in this way, that you can think of it in this way, that assign the flows based on all or nothing assignment. So for every origin destination pair, assign all the demand to the path which is the shortest. Okay. So the second step in this convex combination is to determine the optimal move size. So for this, any interval reduction method can be used. So we have discussed 2 kind of interval reduction methods. One is golden section method, the other one is bisection method. In this case, bisection method might be preferable to use because computing the derivative is easier. Okay. So if you remember, we calculated the derivative of the objective function you want to minimize in the middle of the interval. Okay, and depending upon whether it is positive or negative, we used to discard one of the halves. Okay. So we can use that method, because since the objective function of the user equilibrium involves integral, so when you will taking the derivative of this function z as a function of xn plus alpha times yn minus xn, okay, and then differentiate it with respect to alpha, so then this is the expression you will be getting. Okay, this is easier to evaluate than you trying to evaluate the objective function values at two interior points in the golden section method when the objective function is having integrals in the user equilibrium formulation. Okay. Okay. Now we have discussed that how we can determine the descent direction step. We have also seen how we can solve the move step. Okay, how to determine alpha n. Now one more thing that needs to be discussed is that how do we decide when the convergence is reached. Now when you are discussing the example of convex combination algorithm, we have decided to stop when the difference in the objective function values in consecutive iterations became less than some predetermined quantity. Okay, but since the objective function of Bachmann's transformation does not have any intuitive representation, so we have discussed that. So therefore, when we will be saying that the difference between the objective function values in two iterations become less than some predefined value, then it will not have very physical meaning. Okay, so therefore other convergence criteria can also be used there. One possible convergence criteria is the closeness of minimum path travel times between OD pairs over successive iterations. Okay, so this is what is being said, that when the minimum path travel time between different OD pairs do not change significantly between different iterations of this convex combination algorithm, then we can decide to stop. Okay. So let URS be the minimum path travel time between OD pair RS at the nth iteration. Okay. So if you remember, URS was this variable that we were actually using for minimum path travel time for OD pair RS. Okay. So now for the nth iteration of this algorithm, we are representing it by URSN. So we can decide to terminate this algorithm if, for example, this modulus of URSN minus URSN minus 1 divided by URSN and summing this over all the OD pairs is less than or equal to some kappa. Okay. So this is kind of telling that when the relative difference of the minimum path travel time across all the OD pairs become less than some predefined value kappa, then you can decide to stop. Another termination criteria can be based upon the closeness of the flows over consecutive iterations. Okay. So one way to represent that is in form of this metric, that we are summing over all the links xan plus 1 minus xan whole square divided by this summation of this xan. Okay. So xan is the flow on link A in the nth iteration of this convex combination algorithm. So when this whole quantity becomes less than or equal to some kappa value, then we can decide to terminate. Okay. So there can be more types of convergence criteria also. So the objective is not to list down all of that, but just to provide some examples. Okay. Of course, it is not expected that you remember all of these kind of convergence criteria. These are just some examples that are shown for completeness sake. So therefore, the convex combination method for solving the user equilibrium can be described as follows. So first is the initialization step. Okay. So if you remember, in the convex combination algorithm example that we had seen in the last lecture, we had started with an initial point 0, 0, right. So we need to do the same for solving the user equilibrium problem also. So we need to start with an initial point, but that initial point should be feasible. Okay. So in order to ensure something same here, that the initial point is feasible in the user equilibrium problem, what we can do is that we can perform all or nothing assignment, assuming that the travel times on all the links are equal to the free flow travel times. So TA0 means that the flow through link A when the travel time on link A when the flow through that link is 0. So if you remember, suppose this TA xa is suppose 2 plus xa square. Okay. So, TA0 is then equal to 2, because this is the travel time on this link when the flow through that link is 0. Okay. So, if we assume that the flow through all the links is equal to 0, then you will be getting some travel times, constant travel times for every link. So, with that you can do all or nothing assignment. Okay. So, that will give you some flows through different links. Okay. So, you can use that as the initial solution. Now, why we had to perform all or nothing assignment, and why didn't we just randomly start with some link flows? The reason being that you need to satisfy the constraint that for every OD pair, the sum of the flows on all of the paths that are connecting that OD pair should be equal to the travel demand. Okay, so this thing should be satisfied always. So, one way to ensure is to perform this all or nothing assignment, because when you are doing this all or nothing assignment, we are ensuring that the total flows on all of the paths that are connecting an OD pair will sum to the total travel demand. Okay. So, we have now got a set of link flows that we obtained after doing this all or nothing assignment, when we assume that the travel time on each link is equal to that constant free flow travel times. Okay. So, now we can set the counter n equal to 1 here, and then with these flows that we obtained after the all or nothing assignment, with these new flows you can again calculate the new travel times of every link. Okay. So, suppose this was the you got some initial flows on different links, okay, from this initial all or nothing assignment. So, when you will be putting those flows, you will be again getting new travel times of the links. Okay. So, we use those travel times to perform all or nothing assignment. So, this is now the direction finding step. So, when we will be doing all or nothing assignment based on these travel times that you got in this step 1, then you will be getting a set of auxiliary flows YAN. Okay. Now, we have the solution YAN and we also have the solution XAN. Okay. So, now we can determine this move size alpha n. Okay. So, we can do this line search here. Now, we can use any interval reduction method to solve it. We have seen that bisection method might be easier because the derivative of this function is easier to evaluate as compared to the function values themselves, because it involves integrals. So, golden section method might not be preferable here. And then once we have determined the alpha in this step, we can update XAN plus 1. Okay. Now, if the convergence criterion is met, so whatever convergence criteria we decide, whether we want that the minimum path travel times become close in consecutive iterations or the link flows become close. So, either we can decide to stop then, or whatever convergence criteria we set. Okay. So, if the criteria is met, we can stop, otherwise we can set n to be equal to n plus 1 and then we can go back to step 1. Okay. Okay. So, let us just see an example here for this convex combination algorithm. So, there is this network here where we have 3 links which are connecting this OD pair. There are 3 travel time functions, okay, given for all of these 3 links here. So, in the initialization step here, what we will be doing is that we will be putting all the flows to be 0 on all the 3 links. So, when the flows are all the zeros in all the 3 links, the travel times are what? 10, 20 and 25. That is what you will be getting here. Okay. Now, since the total OD flow is 10 units, so we will be assigning all of that on the shortest path which is connecting this OD pair. Okay. Now, with this flow, we will be again calculating the travel time. So, we put this 10 now here instead of x1. So, we will be getting travel time of 947. Okay. But the travel times of the other 2 links 2 and 3 still remain the same, 20 and 25. Now, in this step we are doing the direction finding step. So, we will be doing this all or nothing assignment again. Now, all of these 3 paths, this link has the shortest time. So, all the 10 units will be assigned here. Okay. And now we get the auxiliary flows. Now we have the auxiliary flow, so now we need to determine the alpha value. So, for that we will be doing that any of the interval reduction methods, and with that we will be getting this alpha, and with alpha, what we get y and these x, we will be getting these x values. Okay. Okay, and in this way we can keep continuing. Okay, so I am not showing the remaining iterations here. So this example has been taken from Sheffy's book on urban transportation network. So you can take a look at this. All of this discussion is being followed closely from there. So this all or nothing assignment for trips in user recurring by convex combination requires computation of shortest paths. Okay. So there are various kind of algorithms for that, label correcting, Bellman, Floyd, Warshall and so on. But this Dijestra's algorithm is one of the most widely known. Okay, so that's why we had discussed it before. But whichever algorithm we use out of these, all of them will give the optimal solution. So the solution will be the same, so it does not matter. So we have already discussed one Dijestra's algorithm for this. And this algorithm assumes that Dijestra's algorithm that travel distances are non-negative, which holds for all the RAID networks. Okay. So with this, we will be ending this lecture now. Thank you.